Hello everyone. In this video, we cover the 1/n fleet insurance. Consider 1/n fleet whole life insurance issued at age X, death benefit of 1 payable at the end of the 1/n year period at which the death occurs. Let Z be the present value random variable for this insurance. If the individual dies in the first 1/n year period, corresponds to the value Kx with superscript bracket m equals 0. The present value is due to the power 1/m with probability 1/m Qx. If the individual dies in the second 1/m year period, Kx bracket m is 1/m, present value due to the power 2/m, the probability 1/m bar 1/m Qx. And if the individual dies within the 1/m year period before reaching age X plus 1, corresponds to X plus m/m. The present value is simply nu, and this is the corresponding probability. And then the pattern continues. Z can be expressed with this expression. And then the expected value for Z, the corresponding present value times the associated probability. In summation notation, we get this expression. The actuarial notation for 1/n fleet insurance. Whole life insurance, AX, 1/n fleet, we have the superscript bracket M. And then the second moment, the expected value of Z squared. This expression, we only change the value of delta in the original expression to 2 delta. And therefore, we have the standard actuarial notation for the second moment with the pre-superscript 2 and then AX bracket M. And then the usual expression for the variance of Z. We also have the 1/n fleet n-year term insurance. The notation, the standard n-year term insurance with bracket M. There are altogether m times n number of periods, the number of 1/n year periods. And therefore, the last possible payment of the death benefit is at the time the individual reached the age X plus n. This corresponds to Kx with bracket m equals m times n minus 1. The corresponding second moment and the variance. Similar expression and notation for the 1/n fleet n-year endowment insurance, as well as the 1/n fleet n-year deferred insurance. And for the relationship, we have the relationship for the annual case where the death benefit is paid at the end of the year of death. Here we have the n-year endowment insurance equals to the n-year term insurance plus the n-year pure endowment. The relationship also applies to the 1/n fleet insurance. And then we have the second set of relationship. The whole life insurance issued at age X equals to the n-year term insurance plus the n-year deferred insurance. Similarly applies to the 1/n fleet insurance. And then the last set of relationship, the n-year deferred whole life insurance at age X linked with the whole life insurance issue at age X plus N. All right, let's take a look at an example. Given that Q30 is 0.02, Q31 0.025, interest rate 5%, deaths are assumed to follow a constant force of mortality between integral ages. And we are asked to calculate the 1/n, M equals 2, for a 2-year term insurance issue on age 30. All right, 2 years. From age 30 to age 32, M equals 2. 1 year is divided into 2 periods. And then the death benefit, the corresponding present value, u to the power 0.5 if the individual dies before reaching age 30.5. The probability is 0.5 Q30. And then if the individual dies within the half year before reaching age 31, the present value is nu. The corresponding probability, 0.5 bar 0.5 Q30. And the pattern continues. In order to get these quantities, we need to add up 4 terms. And this is the expression. All right, so let's do some calculation. We need to get the quantity of 0.5 Q30, and we have a constant force of mortality between integral ages. Therefore, we need to get the value for 0.5 P30. Constant force of mortality between integral ages, we have this relationship. SPX plus T equals PX raised to the power S, given that X plus T is between 0 and 1. Therefore, 0.5 P30 equals P30 to the power 0.5. We get P30. P30 is 1 minus Q30. Therefore, P30 is 1 minus 0.02. We get 0.98 raised to the power 0.5 and subtract from 1. We get 0.5 Q30. The next probability, 0.5 bar 0.5 Q30. We obtain 0.5 Q30. Therefore, 1 minus this quantity, we get 0.5 P30, and we need to get the quantity of 0.5 Q30.5. This equals P30 raised to the power 0.5. Upon calculation, we get 0.009949. And then the next probability, 1 bar 0.5 Q30. This equals P30 times 0.5 Q31. 0.5 Q31 equals P31 raised to the power 0.5. We have Q31. So 1 minus Q31, we get P31. And therefore, this expression and upon calculation, we get this probability. And then the last one, 1.5 bar 0.5 Q30. Similar calculation. 0.5 Q31.5 equals P31 raised to the power 0.5. We get P30, 0.98, 1 minus Q30. And then the second numbers here corresponds to 0.975 raised to the power 0.5. This is P31. P31 raised to the power 0.5. And then last number corresponds to 1 minus P31 raised to the power 0.5. All right, add in the probabilities. Together with the present value. And we get the expectation. The present value multiplied by the associated probabilities. Interest rate is 0.05. Therefore, nu is 1 over 1.05. This is the first term. And we have the second term, the third one, and then the last one. Upon calculation, we get the answer, 0.04178. Let's take a look at another example. We have a 1-year term insurance of 100 issued on an individual at age 50. Death benefits are payable at the end of the quarter of death. That is M equals 4. And then Q50 is 0.06. The nominal rate of interest convertible every quarter is 0.08. Mortality is uniformly distributed between integral ages. Calculate the actuarial present value for this insurance. We need to get this quantity. One-year term insurance, death benefit payable at the end of the quarter of death, M equals 4. And then add in the probabilities. We need to get the value of all these probabilities. (0.25 Q50). Mortality is uniformly distributed. Therefore, we have this relationship SQX equals S times QX, where S is between 0 and 1. Here we have S equals 0.25 times Q50. Q50 is 0.06. And therefore, 0.25 Q50 is 0.015. And then the other probabilities, because the death is uniformly distributed, so we can expect that the probability for the remaining probability are all the same, equals to 0.015. Or else, we can make use of the equation, make use of the formula here. We already get 0.25 Q50. 1 minus this quantity, we get 0.25 P50. And then the second probability, 0.25 Q50, 0.25, we can make use of this expression. We have S equals 0.25 and T also equals to 0.25. Write out the expression. And upon simplification, you can see that this expression can be simplified to simply 0.25 times Q50. The same expression as we calculate for 0.25 Q50 here. And therefore, this probability also equals 0.015. All right, how about the present value? The present value factor for the death benefit of $100 at time 50.25, the present value factor is 1.02 raised to the power minus 1. And this is calculated from the given nominal interest rate. The effective rate every quarter is the nominal interest rate per quarter 0.08 divided by 4, which is 0.02. And nu is 1 over 1 plus I. So here we have 1 over 1.02. So we get 1.02 raised to the power minus 1. And then for the rest of the present value factor, the death benefit remains unchanged at 100. And then the probability is the same at all these 4 time points. So the expected value of this can be written as this. And upon calculation, we get the answer, 5.7116. That's it for today's video. Thank you for watching and see you in the next video.